What's up, Asta? Good to see you, Gabe, as well. And Sid. And Cameron. Wow. I like all the hellos. Those are nice. I will never say no to more hellos. Okay. A couple more minutes. Bonjour. We got some French in there too.
Nice.
Thirsty. What is today's topic? Good question. Today's topic. We're going to be going over electric potential today.
That's dope.
So, yesterday we did electric potential energy, and today we're going to go over electric potential. So, a lot of times in physics, we don't really care about electric potential energy. What we really want is the electric potential, and we're going to see that that comes into play when we start talking about EMF, like electromotive force, and then circuits, things like voltage, current, resistance. Electric potential is a very useful thing. We use it a lot. But okay, cool. Quick announcements. Yeah, one of the homeworks I think was due yesterday, right? Pre-lecture for electric potential is due today at 2 p.m. So please do that. And then I'll probably release a new chapter later tonight or tomorrow. Oh, thank you, LeBron. One second, I gotta turn my Twitch chat off of this. This is why I don't like updating things, dude. They start putting auto activate. Don't put that on there. The paycheck is the only thing that matters to me. LeBron and actually, this is interesting. I was talking to a friend about this because he's like, hey, I graduated from college. I don't know what skills I really have, but I feel like this AI thing is great. Should I start taking some AI boot camp courses? I just want to make money, blah, blah, blah. And I'm like, If you're just doing things to make money, you're not really going to learn them. So I recommended to him, hey, start using AI in your everyday life, or start using it to do cool little projects. And then maybe think about applying to some AI jobs. If you're just going to do an AI boot camp or whatnot. First of all, the AI field is changing so rapidly. It's so quick. Even on ChatGPT's website, their repos, their manuals get outdated after a month because everything's advancing so quickly. So I don't think it's really useful to take one of those courses. I think they're just really money sucks. But anyways, yes, what's the relation? We're going to go over that. So yeah, electric potential and electric field do have a really cool relationship. It involves actually some vector calculus using nabla. We are different. Physics is interesting. It gives us a sense of happiness. Wow. I love that. You're in it because you're in it for the right reasons then. Oh, they sound what's that show? The Bachelor or something. Yeah. Also, yes, thank you to everyone that's sent in your regrade requests. Don't worry if I haven't responded to you. I got them. It's just I will start processing those towards the end of the week. I need to catch up on all the other stuff for this course. Getting all the grades over and doing the first round of grading took a lot of time. So I will get to the regrades as long as you have an email sent to me before Friday at midnight or whatever. I will process your regrade request. And we'll try to get you guys as much partial credit as we can. You love the application of medicine and health. Yeah, there is a lot of physics in medicine and health. A lot of pre-meds start to kind of, doubt physics. Being like, hey, man, why do we have to take this class? I just want to go to med school, become doctor, and, make my parents happy. But there is a lot of physics, and actually there's a whole branch of physics called medical physics. There's also biophysics. There are a bunch of what do we say, like interdisciplinary fields that cross physics with the medical stuff. It's very cool. Heart is just a pump. True. Yeah, fluids. All very true. Okay, cool. Any other questions, feel free, drop them in the chat. We'll go through them. And then, yeah, let's talk about, electric potential instead of electric potential energy, right? Okay, cool. So, earlier, we talked about electric potential energy, which I think we called like UE, right? So, I'm going to say like electric potential energy. And that was equal to like UE, right? And this was calculated as the amount of work it took to like create an arrangement of charges, like to bring all these charges in from really far away and get them to all be nice and next to each other and not moving. That requires work. That requires inputting energy, and doing that increases electric potential energy. That's UE. What we're going to talk about in this lecture is electric potential, which we usually refer to as V, which should also make sense because electric potential, V, is measured in volts. So for once, like, we're using a letter that corresponds to the unit. And this is equal to UE divided by Q, okay? And so what it says is that the voltage or the potential at a place is equal to the electric potential energy of some test charge Q located wherever you're calculating electric potential energy, divided by what that charge is. This definition, it's kind of like, I don't know. It looks kind of weird. But what we really like to deal with is what are called changes in potential, and that's going to be like delta V. And delta V then is equal to, we would say, for instance, like UE2 over Q minus UE1 over Q, which is the same thing as 1 over Q. And then we would say like UE2 minus UE1. So what this tells us is that if I take a charge and I move it between two different situations where we have different electric potential energy, and I calculate the difference in that electric potential energy, and I divide by what the charge was of my little test charge I was doing to probe things, then I will get what the change in the potential is, which is delta V. Cool. The other way this kind of comes about is that you can say that, for instance, the change in the electric potential energy is equal to Q, the charge, times the change in the voltage, okay? We use this, for instance, I think we did it in yesterday's example, but if you have, let's say, an electron, right, that is being moved across a potential, an electric potential. So this is measured in like volts. So let's say, for instance, you have an electron is put across a 300 volt potential. What is its new speed, right? So we could think about having some sort of potential where, for instance, here is like plus 300 volts, and then here would be 0 volts. This is a difference of 300 volts. Well, actually, this would be a negative difference is what I want to do. So actually, let's switch it this way. Sorry. Let's do it this way. This is a 300 volt potential. Okay. Right? Because final minus initial. So in this case, like delta V is V final minus V initial, and that would be 300 minus 0. Okay. And then let's say that you have a charge here, right? And let's say that Q is equal to negative E. all right? You have something here that's just a negative E, okay? In order to create this potential, right, this is going to be positively charged. It has positive potential. This is negatively charged. It has negative potential. And this electric field is going to pull this thing and just rocket it towards this way. And we can calculate what the speed of it would be there, because at this position, you have like electric potential energy. You could calculate what it is, but the main thing here is that the change in potential energy is going to be equal to the negative change in the kinetic energy. So if we remember, for conservative forces, which means no friction, no nothing where like friction is just like rob stuff, then the potential energy plus the kinetic energy is constant. This is also called like, you know, constant mechanical energy. So that means that delta UE plus delta KE is equal to 0, or that the change in potential energy has to be equal to the negative change in the kinetic energy, okay? So, change in potential energy is equal to Q times the change in the voltage. So, in this case, delta mu E is going to equal to negative E, because that's what Q is. And then the change in the voltage is 300 volts. And then that has to also equal the negative change in the kinetic energy. So if this thing starts at rest, right, then KE is equal to 0. And so once the electron gets to the other side of the potential, then you're going to have a positive kinetic energy, and you'll have really fast velocity, right? So velocity here is 0. All right. So then we ended up doing this, and right, the minuses cancel, and you get like 300 EVs is equal to delta 1/2 mv squared, which is the same thing as 1/2 m delta v squared. Student question: the what is this? The quicker the dampening of the system, the quicker it loses energy. Yes, that's correct. Yes. Unless it's overdamped, which we did earlier in the class here. We talked about situations where things are damped so much that they move so slowly that they actually like dissipate energy slower. Critically damped is the fastest way to dump energy out of a system. Okay, but you can solve for V here, because this can be converted into joules, because we say like 1.6 times negative 19 joules is equal to 1 EV. You can divide by the mass, you can figure out the velocity. So this is a practical application of this equation, which gets used a lot, which is change in potential energy is equal to QV, and then this is also equal to the negative change in the kinetic energy of an object. Okay. All right. Any questions about that before we start going on to some other stuff? Maybe I should have asked the classic pre-med question. It's okay, Sensation. It's okay. Sensation's just kind of off topic. It's all right. Sensation, try to keep things a little bit more on topic. It's okay. Feta Guy says, should we be worried? We're going to talk about Nabla, but Nabla is not that scary. I know it's technically a vector calculus thing, and I forget if you are expected to have taken vector calculus before this class. In any case, it's useful. But for all the examples that we're going to do, most of the time, we're going to do like spherically symmetric stuff. So you only have to do the derivative in one direction. Yeah, sure. Okay. Why is it negative KE? Okay. So from this, so if potential energy and kinetic energy add up to a constant, then the change in these things, right? Well, the change in a constant is 0. So that means the change in potential energy plus the change in the kinetic energy has to be equal to 0. And then if you move that over, that means the change in potential energy has to be the negative change in the kinetic energy. Basically, like, if this goes up, this has to go down, right? In order for these things to add up to be constant. And this is just kind of a lazy way of like writing derivatives. Yes. Yeah, we're only I think for this class, I mean, correct me if I'm wrong. If in the homework they start getting a little bit harder with the NABLA stuff, then yeah, we can go over it. But for now, we're usually just going to do stuff in like DDR or like in one direction. So it doesn't. I will show it. I will show like the formal definition of it because it is cool. But okay, that's one way to calculate electric potential. The other way to relate electric potential is to talk about like fields, okay? And so, yeah, the definition you're going to learn here is that and it comes actually from Maxwell's laws. Let's go find Maxwell's laws real quick. Maxwell's laws. When you take upper division E and M, you will 100% do this. But here we go. These are the cool ones. Yes. Or Maxwell Faraday, I guess is what it is. Yeah. And then I want the one with potential in it as well. Okay, we'll take this for now. That's magnetic flux, actually. One sec. Where's it just the E dot dl is equal to change in potential? These are different. One sec. Let me go find it. Yeah, okay, this is what I want. I thought this comes from Maxwell's equations, but the Maxwell distribution, yeah, the same guy, dude. Maxwell is kind of a G. He did a lot of stuff. This is the formal thing we like to talk about. Okay. So the electric field is the same thing as the negative gradient of the potential. So this is the NABLA thing that Fedekai was talking about. This is NABLA. And all NABLA is a derivative in a bunch of different directions, and then you attach like a unit vector on that derivative. So for instance, why is NABLA a vector? It just is. So for instance, if you were to do NABLA v, yeah, do you see how like it's dv dx in the x hat direction plus dv dy in the y hat direction plus dv dz in the z hat direction? You're good, Amelia. Yeah, sorry, there's a little bit of a delay. NABLA is technically an operator because then you'll also learn about other ways that NABLA gets used. Yeah, which is, yeah, this is little. It is called del. It is called del as well. That is correct. Yeah. So this is like for the future. I think mainly you guys are probably going to use this in. Well, actually, we're using this already, so this is cool. So this, we've used Gauss's law, right? Gauss's law is what told us, right, that the integral of E dot dA is equal to, like, here, it's like Q, which is the charge enclosed in a volume divided by epsilon naught. So NABLA is specifically the triangle. There's a couple things. So this is called divergence. This is called gradient. And this is called curl. You will end up doing this in vector cal. I'm pretty sure this is like a vector cal concept, but it is used a lot in physics, especially if you start taking upper division physics classes. You will use this all the time. And you can see this here, right? So this is, for instance, this is the divergence of the electric field. And then this is the curl of the electric field. And then this, I think, some of it comes from Green's theorem, some of it comes from Stokes. But, yeah, they're different properties of it. But we so far have only learned this one. And then eventually, when you take Physics 1C, you will definitely learn this one. I don't know if you'd use Ampere's law. Maybe you do actually. Yeah, curl B. Oh, you definitely use this one. So here, this is for like 1B, and then you are 100% going to use this equation, and I want to say this equation. Oh, and this probably. In like 1C. You'll use these for sure. Yeah, okay. Yeah. But for now, we're just going to do the basic thing here, which is that E is equal to negative grad V. So in spherical coordinates, or like things that are spherically symmetric, such as like point charges, right? We can say that E equaling negative grad V is the same thing as negative, or I think it's partial, negative d dr of V in the r hat direction, okay? And this should make sense, right? Because electric field for point charges, which things that are spherically symmetric, right? Electric field points in the r hat direction. It points like radially outwards, right? So for instance, when you have like a positive charge here, that radiates electric field all out in like what in what we say is the r hat direction. Okay. And you can calculate that electric field from doing the gradient of the potential, or the cool thing about this is you can start flipping the script. So instead of doing E is equal to negative dV dr r hat, you can now move the dr over here, and you end up getting E dot dr is equal to negative dV, and you can integrate. And so cool thing is you get this equation here. The change in potential, right? Because this integral of dV, that's just like V final minus V initial, is equal to the integral of the electric field as you go from like some X initial to some X final. This is the calculus of where it comes from. But for now, yeah, this one we're going to use a lot, and then this one we'll probably use a little bit as well. I don't understand a thing, TBH. Okay, Kyle. Well, let me. It's always good to like see things at least. Good. Where does the r hat go during the calculation? Well, okay. E is a vector, right? Why you can just move it? I don't know specifically. That's probably more of a math question. So E is the same thing as like E r hat, right? Because the electric field points in the same direction as the gradient of the potential. So I believe what happens here is that you can kind of just like cancel the r hat, I guess. Well, E dot dr, right? This points in the r hat direction. Dr points in the r hat direction. So when you integrate that, you should get a scalar, right? And then that's what this, because potential is a scalar, right? Potential is a scalar. Because this is r hat, and then this is also r hat. And if you're dot producting two things together, it's just the magnitudes of them multiplied by each other. Because you don't really care about the directions, because the directions are the same. Yeah. That's also a key thing, right? Electric field, this is a vector. Potential is a scalar. And doing this nabla, this derivative like with a direction, that's what turns this scalar into a vector. Now, I'm sorry. Then for potential, would it be VI minus VF because of the negative sign? Yes. Yes. Okay. Fine. Yeah, because there's a negative sign here. Yeah. Yeah. What I meant to say, sorry, is it's negative and then it's VF minus VI, which is where this comes from. Wait, where was it? Yes. This is it. Yeah. Well, I took this has like the minus sign over here. All right. This goes from VI to VF, and then this goes from XI to XF. So what you end up getting is... No, you're okay. No, the minus signs are important. You're okay. This is the final result. It's good to ask questions. Most professors just wave their hand, and they're just like, shut the fuck up. I appreciate it. Yeah, because it keeps me honest, too, honestly. But this is the main result. There's always like some kind of like you get caught in the weeds sometimes with the minus signs and stuff. And honestly, textbooks are sometimes wrong because of that. But these are the most important things we're going to deal with. Okay. And this also comes down to there's another concept from this that's important. I'm trying to remember how it works. Yes, dot product producing a scalar. Yes. Yeah, because this has to be scalar as well. What is it? It's yes. I think V over D is equal to E. So we say also like for a constant electric field, E is equal to delta V over D. So this is the change in potential. And then this is the distance. This gets used a lot when we have, we're going to go over this later, in later chapters, but if you have like a capacitor. So for instance, if you have like two plates, and let's say this is equal to like plus 500 volts, and then this is equal to, I don't know, like minus 500 volts. Let's say you have like a huge power supply on this. Then you can calculate what the electric field is in between, right? Electric fields always move from positive to negative. And you'd end up getting that E field, right, is equal to 1,000 divided by like whatever this distance is, D. So cool thing you should notice here, right, is that as the distance, right, gets closer between the two, the electric field gets stronger. And as they get further away, the electric field gets weaker. Yeah. So we're going to get into this later. This is like future. And this is capacitors. Okay. I know. Everything kind of seems like a grab bag of things that we're going through so far. Because then it's also all relates to yeah, let me think how I want to talk about this. Yeah. They go through like a formal definition of it, which I can kind of explain it real quick. And then we'll get into like applications of it, because that's really where things are interesting. So if we remember from earlier, right? The change in potential energy is like equal to the negative work done by the field, right? Remember when we had this? We said, yeah. This should be delta, honestly. They should have written this as delta. Unrelated note, if we're still confused about how to take the surface or volume integral electric field, yeah, just come to office hours. I'll go through it. That's totally cool. So this was also equal, right, to like the negative work, right, done by the field. And remember that work, right, is equal to force times distance. Yes, totally cool. All right. Then the other thing we learned, right, is that the force on an object, on a charge, right, is equal to Q times the electric field, right? So now you're able to do this. You can say, okay, cool. Well, force on something is the charge of it times the electric field that it's in. Okay, so then you get to here. And then we also defined, right, that electric potential energy divided by Q was equal to potential. So V is equal to UE over Q. I don't know why they're writing U. Well, oh, they're saying it between position R and P, whatever. Okay, so if you move that over, now you have like UE over Q, which is equal to V and this should be delta V is equal to this. And that's our original result that we had from here, right? Where was it? No. Yeah, up here. Change in potential is equal to the integral of the electric field times the distance that something travels along an electric field. They do then the example, for instance, for a point charge, okay? So if you want to think about the potential yes, per unit charge, correct. It's related. Change in electric potential, or I see, yeah, change in electric potential is like integrating the force. And yeah, electric force isn't on a per unit charge basis. Force is just in newtons. Yeah, nice. It is related to the charge. Okay, potential for a point charge. Correct. Yes. Yeah. Okay. So so for a point charge, right? If we use our original definition from here, so the potential at some point P, or basically the change in the potential at some point P, is equal to the integral, right, from one location to your point P of E dot dl. For a point charge, we remember that E is equal to 1 over 4 pi x epsilon naught, and then this was Q over R squared. Right? This was electric field for a point charge. And we got that from Gauss's law, right? Good. I'll show you where the significance is. Because potential is all relative, Fedekai, okay? So P and R are just two different locations, all right? And then this is the potential at P referenced to what the potential was at R. So in the case of a point charge, what they do is they say, okay, here, I have a point charge. Let's say this is Q, and I want to figure out what the potential is located at some distance P, according to their terminology. So I say V of P here is equal to what? Like, if I'm a distance P away from a point charge, what is my potential there? What I can say is, like, okay, well, the change in potential is equal to the negative integral from some location to a location P of E dot dl. So in this case, right, we're going to take the electric field all the way out at infinity and then bring it in to the electric field at some position R. This right here is the same thing as Vp minus V infinity, because that's equal to delta V. And this is equal to going from infinity to some point P, and then it's the electric field, 1 over 4 pi epsilon naught, times Q, right? Because that's the electric field created by a point charge. R squared, and then dr. You take it from like infinity, not from 0 to infinity. You take it from infinity to a point. The reason why we do this is that we define zero potential to be infinitely far away. Whenever we did stuff with gravity, right, we defined zero potential to be on the ground. And then with the spring, right, zero potential was when the thing was at equilibrium. With electric stuff, we tend to say that all the way out, infinitesimally far away, that's where I have zero potential. So anytime I'm measuring a change in potential, I'm measuring it referenced to me being really, really far away. So if I'm measuring the potential at a position, I really, dude, this textbook fucking sucks. I hate how they're changing numbers so much. They should not be changing the variables so much. I'm going to go fix this. I hate how they keep just saying like R and P, like stop. Okay. This is out at infinity, is what it is. Okay. Exactly. Right. Yes. So delta V, I'm fixing this. Delta V is defined as going from some position 1 to some position 2. Yeah, when the molecule's really far away, the potential is 0. Correct. Yeah. So what we like to think about is like, so bring in from way out at infinity. Because when we calculate delta V here, that's VP minus VR. VP minus VR is the integral from R to P, because this is your initial. This is your final. And then delta V, right, is always like V final minus V initial. And we always take our initial position to be all the way out at 0. All the way out at infinity, because then I know that this, right, at infinity, V is equal to 0. We define zero potential to be all the way out at infinity. Anyways, okay, so you integrate this, and this ends up getting you 1 over 4 pi epsilon naught q over, well, there's a minus sign, right, because it's 1 over r squared, so it's negative, and then it's 1 over p minus 1 over infinity, and then this is 0, so then you just get 1 over 4 pi epsilon naught q over p. Or you could say that like v is a function of r is equal to k q over r. And this should look pretty cool, right? Because remember that like grad v is equal to negative, is that what we said? Grad v is equal to negative e? One sec. Yeah. No. Yeah, grad v is equal to negative e. And so this tells me that, okay, cool. So negative d dr of kq over r in the r hat direction is equal to negative e. And the derivative of 1 over r is negative 1 over r squared. Wait, I put too many negatives. Sorry. So this gets me negative kq over r squared is equal to negative e, and this is in the r hat direction. So then e, which is a vector, is equal to kq over r squared, r hat. This is our original electric field for a point charge. It's just showing that it's consistent, right? And this is just a calculus thing, right? Because we're just taking like the derivative of an integral, which should get me back my original function. But yeah, in general, when we're calculating potential, we're always referencing it to 0 potential out at infinity. So when you do your integrals of E dot dl, you want to usually start at infinity and then come into the position where you're at. Where did the 2 go? What 2? Was there supposed to be a 2 somewhere? This is just a single point charge. Yeah. If you take the derivative of this, this is to the -1 Fedekai, so then it pulls down, it's negative, and then it's negative 2. So then this is why it's r squared on the bottom. Yes. Okay, and that's also, we talked about, yeah, here. E is equal to delta V over D. Yeah. This textbook doesn't do a great job of, like, dropping deltas. I get it. They're trying to... I hate this too. It's like they're assuming. They're saying, like, oh, when we talk about potential, we're always referencing it as a delta potential to 0. And I'm like, okay, but what if I need the potential between 2 different points? Now that needs to be a delta. It's not just V. I'm going to fix that. I think I'm going to fix that. Okay, cool. Okay. Right. And so a question you might be asking is, like, why the hell are we doing all this? why are we calculating all these different things? It's worse than those. It's just shorter. Yeah. It's a little bit more concise. Also, it's free. I mean, well, not free, but it's very cheap, right? It's only like $20, $25. Okay, yeah. The reason why we even come up with the concept of potential, right, like voltages and things, is that given that we know what the charge distribution of certain shapes are, like given we know what the electric fields, we can then come up with graphs for, like, what the potential looks like. And that tells us a lot of interesting things, especially in the forms of like electricity and Van de Graaff generators. Yeah. And also, like, whenever we use, like, voltmeters and stuff, that's all measuring potential. It's all voltage. So the example they do here is also the a Van de Graaff generator. This is cool. Anyone seen a Van de Graaff generator before? It's kind of like a Tesla coil. Yeah, EKGs, right? That's all in voltage, yeah. So what this does is you can measure the potential on, let's say, like this metallic sphere, and that voltage is related to how much charge is on the sphere. And then what happens is, like, once this voltage gets to a high enough value, it will eventually allow charge to, like, arc across the air. And that's why you can get these, that's how lightning works, by the way, yeah. So using our equations to calculate potential, we can figure out, like, what the electric field is created by stuff, and then we can also figure out how much charge is on an object based on just measuring its voltage. Looks like a machine electro boom would make. Yeah, like welding. Yes, good. Welding is another great example of this. Yes. Welding is creating really high potentials, and then things are arcing. Yeah. I don't know if I want to go over dipoles. That's a really messy derivation. Okay. But in general, what we've learned so far, right? Electric field, just, like, sum things up. For point charges, this is a vector, right? And this is equal to 1 over 4 pi epsilon naught. And then this is Q over R squared in usually some direction. We say like the R hat direction. And then potential is equal to 1 over 4 pi epsilon naught. And then this is Q just over R. And that's in the R hat direction. Okay? Oh, no, sorry, that's not in a direction. That's just R. This is a vector. This is a scalar. So when we're measuring electric fields, those have directions. And usually with symmetric spherical things, that's just in the R hat direction. But at these positions, you can also measure what the potential is. And then the relation between these two is what we did earlier with the integrals and the derivatives. So in physics land, when you have to calculate things for like homework, you're usually either like given one of these. You're either given the electric field and you have to find the potential, or you're given the potential and you have to find the electric field. And so going from E to V, you learn that negative E dot dl is equal to delta V. And then going from V to E, we learn that nabla V is equal to E. Or was it negative nabla V? Sorry. I gotta remember. These cursed, yes, it's negative nabla V. Okay, cool. Yeah. So these are the relationships. So these are the important relationships that you need to know. So if you're given one, you can usually find the other. All right, let's see. If I have time, I'll also do, equipotentials and stuff. Good. If you have the potential, how do you get the directional information of the field? Okay, because you need to see how the potential varies as a function of different directions. So this will end up pulling out what direction the electric field is. Because remember this in spherical. Well, here, let me just like pull it up just so I can have them. Nabla in different coordinates. I just want an easy one. What? Has no one on Google just like easily done these? I don't really want to have to do these, but fine. Okay, fine. I'll do it. Okay. So and this is again, this is a vector cal thing, but like so in Cartesian, del A or grad A is dA dx x hat plus dA dy y hat plus dA dz z hat. And then we say in spherical, so this is the case of things being, spherically symmetric. Then it's r hat, theta hat, phi hat. And then these are some different constants that come out. And then let me get cylindrical. Cool. Yeah, that's what it is. Well, that's even good. Okay, I hate that this is not. It's a little blurry. No, this is in cylindrical. Okay, let's see. Fedagai says, so you would not only be given the potential about a specific point in space, but an equation. Hence, by testing the variations of V due to position, you can reverse. Exactly. So you would need to be given the equation of the potential as a function of different variables. So for instance, usually like V is just a function of R. So that when you take the gradient of it, right, you end up pulling out this term in the R hat direction. If your potential does not vary in a certain coordinate, then the gradient component of that will be 0, right? Say, for instance, like your potential was equal to like, I don't know, like 3x plus 5y, and then that's it. Then when you did gradient of your potential, you would only get, for instance, you would get 3x hat plus 5y hat plus 0 z hat. So now your electric field, you know, only points in the x and the y direction. Yeah. Basically, like, whatever variables your potential depends on, that will dictate what directions your electric field points. So, example. And the dimensions of the variables at V depend on its direction that your E... Yes, correct. Yeah. Well, by definition here, right? So when you do this, E dot dl, okay, then the path that you take, the direction of that depends on what the direction of your electric field is. Which is actually kind of a cool thing. So this is why, like, equipotentials exist. So this is the same thing as just like same V. So say, for instance, you have a point charge, right? And you have two different locations you're looking at, location A and location B, all right? We know for a point charge, that's going to radiate an electric field that's in this direction, right? This would end up being E. And then if I wanted to, for instance, do... See, now they put the delta. If I wanted to figure out what the change in the potential was going from point B to point A, right? That means I would be integrating, right? This is the same thing as negative integral, right, of E dot dl. But E points radially outwards, right? In this case, this points in the r hat direction, but dl would point in the theta hat direction, right? This would point in like the theta hat direction because this would be dl. And notice that the electric field is then always perpendicular. So r hat is always perpendicular to dl, which is theta hat. So those two dotted with each other gets you 0. And this is why we would say that, oh, the change in voltage is equal to 0. So that means the potential here and the potential here are the same. And that's called an equipotential. Okay? There are a lot of concepts to this. You know what I think I'm going to do? So we are going to move forward after this. I'm going to get into, just to fit with the schedule, we're going to start doing capacitors tomorrow's lesson, and then we'll keep doing like 2 days per lesson. But on that last week, I'll have basically like filler days for things that I wanted to explain a little bit more that were relevant to each topic. I want to make sure we get through everything so that we're not rushing at the end being like, oh man, like we're screwed. We got to like, finish up all the chapters. But that last week won't be just all review. I will also use those days to like go into like more advanced topics within each thing. Because there's a lot of cool things with potential that I'm not able to teach you in just an hour and 15 minutes. But yeah, that'll be my plan. So so the equipotential is just when the change between points A and B is 0. Yes, good. How do you know the direction? The direction can be whatever you want. DL can, this is path independent is technically what we're saying. Path independent. So what that means is that like whether you decide to do this or whether you decide to do this, the value of this integral will be the same. And so in this case, I'm conveniently choosing to go in an arc that is always perpendicular to the electric field. So my path dotted with my electric field is always 0. And that means that the change in the potential between point B and point A is also 0. You get to choose whatever direction you want, but in physics, you start noticing patterns. We have like certain nice things we like to do. And it's usually revolving around some sort of symmetry or some sort of like the dot product is always 0 or the cross product is this. Okay, let me see. I think we got, let me see what clicker questions we got. Okay. Question 1 here. Yes, we love the clicker questions. I need them. I need like some wins today. I know. If you're confused, I understand. I totally get it. It's trust me, this is a lot of content to try and cover in one lesson. Again, come to office hours. Let me help you explain it and work through it yourself. Like the homework questions, I learn a lot better by doing. So if you try like doing these things or like again doing these clicker questions, things should make a little bit more sense. Okay, a 1 centimeter plastic sphere used in static electricity demonstration has a charge of 21.5 picocoulombs uniformly distributed at its surface. Okay, so some cool things here that I'll just talk about. This is technically a insulator, right? Plastic is an insulator. And uniformly distributed, right? That means the charge is throughout the sphere. But they want the potential near the surface. Okay, so here we have our sphere, and then here we have our radius, which is 0.01 meters. And I'm trying to figure out potential. So I'm going to figure out V. V equals what? So the quick way to do this would just to be say that like, oh, V equals KQ over R. Because once you are outside here, you can kind of refer to this whole thing as just a point charge with a charge of 21.5 picocoulombs. But let's not do the shortcut. That is what the shortcut is. Oh, 1 centimeter diameter. Thank you. Yes. Good catch. I read that wrong. That's just mean. Why? Why diameter? Just give radius, dog. Who measures the diameter of spheres? Okay, fine. There we go. Okay. Let's calculate, for instance, what the electric field would be. So E field for R is greater than, let's call this like big R. Right? We know that's E times 4 pi R squared is equal to Q enclosed over epsilon naught, and then the charge that's enclosed, right? When we're a distance r away, well, that's just the whole charge, right? The whole 21.5 picocoulombs. Okay, so that tells me that E is equal to 1 over 4 pi epsilon naught, and then that's going to be 21.5 times 10 to the minus 12 over r squared. This is my electric field, right? And this is in the r hat direction. So then if I want to calculate potential at some location r, where r is outside the sphere, right? The key thing here is, right, the electric field is not this when we're inside, right? That's because we start enclosing more charge as we start moving more through the sphere. We did that, I want to say last week. I can do this. So I can say, okay, change in potential, which is going to be V at position R minus V at infinity is equal to negative integral, and then that's going to be from infinity to R of E dot dr. Okay? This is 0. And so we say VR, or like V at position R, is equal to negative, and then this is infinity over R. The electric field is 1 over 4 pi epsilon naught. Let's just write that as K. This is also just K. And then 21.5 times 10 to the minus 12 over r squared dr. So then when you integrate this, right, minus comes out, and you just get K 21.5 times 10 to the minus 12. And then that's 1 over r from infinity to r, which, cool, that one goes away. 1 over infinity is just 0, right? Infinity to r, correct, yes. So we're calculating the change in the potential, right? Which is like some final position and some initial position. We're choosing our initial position of where we're calculating potential to be way out here. This is like the initial, which is where like r is equal to infinity, and we are defining potential here equal to 0. Okay, we're defining that 0 potential. Same way like when you do gravity, right? You define like h equals 0 here. You have to define somewhere that potential is 0. Well, to go from infinity to r, that means my position needs to go from here, infinity to r. If it is, or whether we can just do the easy version, if you're finding the potential outside of this, then yes, you can just assume that this is a point charge, and then you can just use this equation. I'm going to show you get the same thing here, right? So look at this. This is just K Q over R, right? Which is the same thing we got here. Exactly, yeah. So this is, right, this is the same easy result. Where this does not apply, Sophia, is if I ask for the potential like inside here, or if you have like nested things, okay? In that case, the potential isn't just a point charge. You can make some assumptions and things, but okay. All good. All right, so let's just solve this. So V is just equal to KQ over R. So K is 9 e to the 9th. And then Q is 21.5 e to the minus 12. And then we're dividing it by, good call there, it's 0.005. And so that gets me 38.7 volts. Okay? So that's choice C. Nice. Good. All right, let's do the next one. Okay, we say consider the region with a non-uniform electric field that points in the x direction. The equipotential lines are shown in the figure below, along with the plot of the electric potential as a function of the position along the x-axis. Which of the statements is false? Okay. All right. So, okay. I don't really know what this graph is, but I guess they're saying here at A, you're at 10 volts. Cool. Here you're at 50 volts. Okay. All right. The electric potential at B is greater than the electric potential at A. Well, that is true, right? Electric potential here at X equals B, that's like 40 volts versus 10. Okay, so I'm cool with that one. The electric potential at B is less than at C, also true. Ooh, here we go. The magnitude of the electric field at B is greater than the magnitude of the electric field at A. So this is where we have to remember our relationship between electric field and electric potential. So what is it? E is equal to V over D, or we say that, or negative Negative V over D, I think is what it is, right? Or let's do it with our where is it? This is our thing. I want to use this. Yeah, we're gonna use our let's use our full vector calculus definition here. Okay. So we know electric field is equal to the negative gradient. This is in 1D. This is just the slope. In one dimensional, this is the same thing as like ddx basically, where x is your one dimension, the one direction you're looking at. So where's the slope greater? I would say the slope at B is greater than the slope at A, so the electric field should be greater there. Yes. So that's true. Or we're saying the magnitude. Wait, which of the following is false? Oh wait, this didn't copy out correctly. 1 sec. There we go. 1 sec. Let me fix this. It was missing. No. Okay, there we go. This is what I want. I want all these choices. Okay. So we said A was true, B was true, C is true. The magnitude of the field at B is less than the magnitude field at C. That's false. Correct, Fedekai. Yeah. We're mainly going to just deal with 1D stuff. So this one's false. B has a very, very, very slopey slope. It's got a very steep slope, right? So that should have a very high electric field. Electric field at A is greater than at C. That's also true. I think this is... Well, actually, they're probably equal, honestly, right? This looks like this is equal. But I guess it's technically bigger than this. Okay, so whatever. We'll call this true. Correct answer is D. Does that make sense? Why that correct answer there is D? Cool. Thanks, Asta. Because of the slope. Good. Very good. Very good, guys. Because of the slope. Okay. So now let's do this one. Ooh. Okay, consider a region of uniform field as shown below. Points B, C, D, and E are all a distance D away from point A. Okay. And we're trying to figure out moving from A to what point results in the largest positive potential difference. Okay. So let's remember that potential difference, delta V, is equal to negative E dot dr, right? So let's think about it. If I go from A to E, well, in that case, let me make this a little bit thicker. Yeah, yes, time. Time is the #1 thing, but we don't have a lot of it. It's the summer. Okay, going from A to E, right? Your dr is pointing this way, but electric field is pointing this way. So those are perpendicular to each other. So the dot product of that is 0. So this is wrong, right? This is 0. That also means going from A to B is also 0. Okay, C and D. All right. Electric field is pointing in this direction. So if you want the positive potential difference, you want these things. So if you want delta V to be positive, you need E to point in like this direction and dr to like point in this direction, right? So I believe you want to go to the left, because in that case these things will be 180 degrees with each other. And so yeah, that choice is going to be, that's D. Right, so it's going to be this one. You can kind of think of this, right? If you're a positive charge here, right? and you have an electric field that's pointing from here, right, positive to minus, you're not really gaining any potential moving downstream. Like moving with the stream, you're not really gaining any potential, right? But if you're going against it, you are. You're gaining electric potential energy, right? Which is also technically related to potential, because electric potential energy over Q is equal to V. This is also why, for instance, if this was a negative charge and you moved this way, you would still have a positive voltage or a positive potential change. Because your potential energy would also be getting like more negative. Okay, so that's D. Got it? Nice. Okay. Ooh, last one. This is what I talk about the graphs. Yeah, this is cool. I'll see if I can explain it. I don't know how mathy I want to get with it for the next 3 minutes. But okay. All right. Charge Q is spread evenly on a thin spherical shell of radius r, which represents the best electric potential as a function of the radius. Okay, cool. So if Q is uniformly spread, right? This means it's an insulator, right? If it was a conductor, then the charge would only be on the outside, right? So we remember, right, for a spherical non-insulating shell, insulating sphere. Correct. No, you will gain electric potential. Yeah, you'll lose potential. Yes, yeah. Okay, so for spherical insulating sphere, right, we had E was equal to K. Well, okay, it was E 4 pi r squared, and then that was equal to r cubed over r naught cubed, and then it was Q, right, over epsilon naught. So then that was E is equal to K, and then it was like R over R cubed. Yeah. We did this earlier. Basically showing that the electric field, if you're in a non-conducting sphere, the electric field goes up as you get out. If this was conducting, right? If it was conducting, E equals 0 inside the sphere, because all the charge is only on the outside. If you're going with the stream, will your let me do that during office hours, Fedekai. There's too many double negatives that I have to remember. And I want to wrap this question real quick. Okay. One is non-coding DNA. Wrong class. Okay. So this is the electric field. So it goes up as a. So here's the cool thing. We could graph what the electric field is, right? We know the electric field will be linear as we go out, right? To let's say this is E, right? To out all the way out to big R naught. And then once you're outside the sphere, right, you treat this as a point charge. So we say like outside E is just equal to KQ over R squared. So it ends up looking like this. Okay. That's the electric field, which is not the potential. Because the potential is equal to the negative integral, right, of the electric field, dr. Then usually, right, we go from infinity out to r. So once you get here, yeah, so coming this way, right, from infinity to r, you're going to start gaining more and more potential. So all these kind of make sense for outside, right? We also know for a point charge that V is just equal to KQ over R, right? So all of these on the outside make sense. However, we got to think about like what happens as you start going from the outside of the shell inside towards the center. Well, the potential is changing as we come inside, right? Because the electric field is changing. Remember that what you're doing is you're adding up the electric field as you're moving in this way. So here, yeah, you start adding up more, and that's why the potential starts going up. But then here, you start adding up less and less and less. And it's, you know, integrating this is not going to be linear. Or actually, wait a minute. Sorry, one sec. Wouldn't your potential approach infinity if your R is close enough to the source of the field? Yes, but the electric field there is 0. Right? Remember how we were doing this? Right? When R is equal to 0, then the electric field is 0. I think potential should increase as you're coming in. Oh, wait, I'm being really dumb here. Sorry, we don't even have to do the integral stuff here. Sorry. Let's remember from this. Let's remember from here, right? Where was it? Yeah. Grad V equals E, right? Was it negative grad V, right? So if the electric field is increasing, wait a minute. Why is that constant? Oh. Sorry, I misread this question. Thank you. Okay, sorry. It's, okay, this is written poorly. Spread evenly, we should say on the surface. God damn it. They just say, okay, they also say it's a shell. I should have read a shell. A shell means it's hollow on the inside. Okay. There we go. Okay. I was doing it for a insulating sphere. Yeah, okay. Yeah, this is fucked. All right. All right. Outside, yes. Inside, it's just inside. E equals 0. Okay. So, this is what it should be. There we go. Okay. I figured it out. This is the E field. Right? And now, yes. Changing potential is equal to negative integral from infinity to R. It's 0 because we say it's a thin spherical shell. A shell is hollow. And if the charge is spread on the shell, that means there's no charge inside. They didn't talk about any point charges on the inside. Yeah, that makes a lot more sense, right? Yeah, okay. So as you're coming in this way, you start adding more and more charge, right? So your electric potential should be going up. And then once you get to here, now you're adding up a bunch of 0. So adding zeros does not change your potential. And so this is why this is this, right? Because this is inside. You're not in. So here we say like inside. No more E. Also, remember, negative grad V is equal to E. You can kind of do the reverse, right? So the derivative of this is 0. And then the derivative of this is decreasing. But, oh, it's the negative of that, so that's why it does this. Yeah, okay, cool. You could have done it two ways. You could have drawn the electric field as a function of position, and then integrated backwards, or you could have taken the potential, taken the derivative, and see if it matches your electric field graph. If there's no charge inside, then could the field still point inside, though, since the field points in all directions orthogonal to the surface? No. Because by Gauss's law, E dot dA equals Q enclosed over epsilon naught. So there is no electric field inside. Because you have no enclosed charge. Yeah, it's the same thing if this was... This is not an insulator. I saw evenly, and usually that means insulator. So this actually means it's a conductor. Okay, sorry, I really went over time here. Okay, correct answer is gonna be choice 3. Which, let's see, did we make that? Can we think of this as a symmetry problem? Yeah. Yeah, you can probably think of it as a symmetry problem. Okay, see? Let's do it. Get it right. That's right. One more thing. That long way for the earlier was just deriving electric field with Gauss's law. Correct. Yes. Yes, maybe by symmetry too, Fedekai. You're right there. Yeah. Oh, you're talking about like this one. Yeah. Yeah, this was using... So this right here, this came from Gauss's law. Right, Sib? The electric field from a point charge. And then we use that to integrate to get to this, which is the same thing. This is always just... This is like the cheese, like, easy shortcut. For point charge potential. Okay, cool. All right. I took a lot of your time, but I hope you guys learned some stuff. This is a very complex topic to all do in one day. But yes, glad. Okay, come by office hours if you have more questions and you want to go over things. That's in 2 hours. So I'll be online. Feel free to ask whatever. We'll go through it. And we'll see you tomorrow. Same time, same place. Enjoy. Happy Tuesday.